everyone, welcome to Try Right, the new era of learning. This is Pack 365. In Module 2, we are discussing about Constant Satisfaction Problem, CSP, in Artificial Intelligence. Let's begin the topic. Constant Satisfaction Problem. A constant satisfaction problem is a mathematical problem where the solution must meet a number of constants in CSP. The objective is to assign values to variable such that all the constants are satisfied. Many AI applications use CSPS to solve decision-making problems that involves managing or arranging resources under strict guidelines. Common applications of CSP includes. We all know that construct satisfaction problem are a fundamental concept in artificial intelligence and operation research, right? So they provide a powerful framework for modeling and solving problems, where the goal is to find a solution that satisfy a set of specific conditions or constants. So here the CPS includes scheduling. It assigns the resources like employees or equipment while respecting time and availability constant. So in scheduling, we most consider employee shifting scheduling, university timetable, flight scheduling, project management, task dependency or deadlines. Like we schedule the anything that we schedules and planning, organization task with specific deadline or sequence. So planning logistic and delivering route optimization in robotic path planning, talk allocations, resource allocations, distributing the resource efficiently without overrush. So usually distributing the limit resources, example, equipments, bandwidth, uh, especially like that. In this we are in the resource allocation. So we can say we have the puzzle solving, Sudoku like and Queen problems, and we have crossword puzzles and configurations and automated reason systems and computer variations. CPS provide a powerful mathematical and computational framework for tracking problems, where the solutions must either to specific rules and limitations, make them a constant in the intelligent systems. Here we have components of the construct satisfaction problem. Here we can say that variables. Those are the things we need to find for value. We need to find values for each variable represents something that need to be decided. For example, in Sudoku puzzle, each empty cell is a variable that need a number. A variable can be of different types like yes, no, choice, a boolean with a whole number, integer, or categories like color or name. Those are the unknown elements in the problem for which we need to determine values. They represent the decisions that need to be made, right? So, example in Sudoku puzzle, each empty cell is a variable, right? So the goal is to find number of for each of those empty cells. We have the type and the types for variables can hold various types of values like boolean, yes, no, and a whole number like integer, number, and categorize name, example, color, red, green, blue, like that. And we have domain. This is a set of possible values that a variable can have. The domain tell us what value we can choose for each cell must contain one of those numbers. Some domains are small and limited, while other can be very large or very infinite, right? So, for example, for each variable, its domain is a set of all possible values that variables can take. It efficiently tell us what option are available for each decision, right? So, example again in Sudoku, we can take like that. For any empty cell variable in a Sudoku puzzle, its domain is a set of number for 1 to 9, right? Uh, we have a 3 into 3, 9, and 9 into 9, 81 cells overall the table. So, because each cell must contain one of those numbers. And the size is domain can vary greatly in size, small and limited, like 1, 2, 3, or true or false, very large or even infinite through a practical CSPS domain, or often finity to allow for computational solutions. And we have finally construction. So in the construction, they are the rules that restricts how variables can be assigned. Values constants define which the combination of values are allowed. They are different types of constants, right? So in this we have those are the rules of restrictions that dedicate to variable can be assigned the values. They define which combination of the values are permitted and the which are not. Constant on the satisfaction are part of the constant satisfaction problem. Types we have there are different types of constants and discussed in the previous explanation like unary, binary, higher order. And but the core idea is that they limited the choice of values of our variables, often the relation to other variables. So the goal is to the ultimate goal of following a CSP is to find an assignment of values to all variables such that all constants are the simultaneously satisfied. So a CSP is defined by what you need to decide variables, what choice you have for each decision domain, and uh, and what rules those choose must be following constants. So here we have about unary constant applied to a single variable like the cell cannot be 5. So the constant applied to a single variable that restrict the value that a specific variable can take independent of the other variable. Example like the cell is cannot be 5. This means that for a particular cell variable, the value is 5 is not allowed in this domain because uh, it is already required by some other number. And next, uh, binary constant. Binary constant involves two variables. Like these two cells cannot have the same number. The constant involves two numbers. They define a relationship or restrictions between the values and assign it to the pair of variables. Example, like we take from image, those two cells can have the same number. This implies that if you have two specific cells variables, say x and y, then the assigned value must be different. X is not equal to y, and this is a very common type of constant in puzzling. Like so, example, two cells in the same row cannot be the same numbers. Like one cannot be two, two cannot be one, like that. And higher order constants involve the three of or more variables. Like each row, if Sudoku must have all number from 1 to 9 without repetitions. So those contracts involves three or more variables that they specify relationships or conditions that must hold true from a group of variables simultaneously while they cannot often be decomposed into a set of binary constants. Sometimes expression they may higher order constants simplify the problem represents, and we can say that. So example for in this image, we can say that in like each row in the Sudoku must have all numbers, right? From 1 to 9 without repetition. This constraint involves all 9 variable cells in a like specific rows. It is a powerful constraint that ensure uniqueness and completeness with that the set of variables. Essentially, meaning means that for any given row, the set of number assigned to each cell must be exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, like only up to 9. So here we have the types of constant satisfaction. So here we have the first, here we have to say we have binary. CPS can be classified into different types based on the constants and the problem of characters. So we have binary CSP, binary constant satisfaction problems. So in these problems, each constant involves only two variables. Like in a schedule problem, the constant could specify that task A must be completed before task B. So in those problems, every constant involves only two variables. This means all the relationship and the restrictions are expressed has pairwise interactions. In scheduling problems, the constant could specify that task A must be completed with before task B. There is a binary constant because it relates on the two variables, task A and task B. And we have another non-binary constant satisfaction problem. Those problems have the construct that involves more than the two variables. For instance, right, in a setting arrangement, problems a constant could state the people cannot sit next to each other. So this problem contains the constants that involves more than two variables, like higher order constant, or while higher order constant cannot often be converted into equal set of binary constant. Sometimes by introducing auxiliary variables, it's often more natural and clear to express them directly as a non-binary constant. In a sitting arrangement problem, a constant could the state of the three peoples cannot fit in the each other. This is a constant involving those variables, the three variables, like the three peoples, we can say that. Hard and soft constants. Hard and soft constants must be strictly satisfied, while the soft constants can be violated. But a certain cost, this is often used in real world applications where not all the constants are equally important, right? So those constants are the must strictly satisfied in if the solution is violates even one hard constant, it is not considered a valid solution. Most traditional CSPs deals with executive with hard constant. So soft constants, those constants can be violated, but typically at a certain cost or penalty. The goal in a problem soft constant is to find a solution that satisfies all hard constants while minimizing the cost incurred by the violating soft constant. And in real world relevance, this distance is very important in real world applications. Uh, because not all the constants are equally important for the instance. Scheduling the ensuring a meeting ends before and another must be hard constants. But minimizing the walking distance might be a soft constant. So next we have the representative of constant satisfaction. So in CSP, it involves the more interaction of the variables, domains, and construct below the structure represented, right? Of how CSP is formed. So we can say that a CSP is a formally defined by the interaction of the its three core components like variables, domain, and construction. So find a set of variables which we can say that find a finite set of variables. We can have v1, v2, and vn, right? So the problem consists of a set of variables, each of which needs to be assigned a value that satisfies the given construct, right? So the problem is begin when they defined a set of variable. Each variable is an entity for which a value needs to be assigned. So the goal is to find the values for all those variables to that satisfies the given constants, right? So here we have non-empty domain for each variables d1, d2, dn. Right, the whole variable depends on the variables, domain, and constants. So here we have the domain variables d1, d2, dn. Each variable has a domain, a set of possible values that it can take. For example, in Sudoku puzzle, the domain could be the number 1 to 9 for each cell. So every variable vi has a corresponding domain like di, uh, which is non-empty set of all possible values that vi can take. For each cell in Sudoku puzzle, the domain is the set of number of 1 to 9, right? Finite set of constant like C1, C2, and Cm. So here we have scope and relationship in it. Constant restricts the possible values that variables can take. Each constant defines a rule or relationship between the variables. So each individual constant Ci is typically represented as a pair of scope and relationship. So at the scope, this is a set of variables that are involved or in this particular constant. For a binary constant, the scope would be two variables. For higher order constants, it would be three or more. In relationship, this specifies the actual rule of the constant. It a list of all valid combinations of the values for the variables in the constant scope that satisfy the constants. Any combination of values for those variables not in this relationship would be violent to constant. So we have here another variable constant. So same as the same as say like a set of constant representing same values like it's set of the relationship in scope and variable. So scope is for variable that are involved this particular constant for a binary constant, right? In relationship, the specify the actual rule of the constant. It list of the all valid combination of the values for the variables. So in this we have scope and reasonability. We already discussed that the set of variables involved in the constant, a list of valid combination of variable values that satisfy the constants. Right. Here we have the solving solving constant satisfaction problem, especially. So we have the three constants like backtracking algorithm and forward checking algorithm and constant propagation algorithm. So usually backtrack algorithm, it is a concept used to most basic common algorithm for solving CSPs. It is a systematic search algorithm that employs possible assignments of to the variables one by one. Like how to it works, like it starts by assigning a value to the first variable, then it moves to the next variable, assigning a value. This is consistent with the previous assigned variables, does not violate any constraints involving be already assigned variables. If it is reached a point where it cannot assign a consistent value to the current variable, because all the possible values if domain violate a constant with a previously assigned variable, right? So it backtracks again. So this means it is a unassigned the last variable, goes back to the previous variables, and the three are different variables for the variables. So in this process, the continues until the completion, and the it will be find a proper goal state. So usually backtrack is useful when we can completely reach to the dead end of the node or dead end of the path. We can usually backtrack and we can do a move and we can choose another path. So we have the forward checking algorithm. So in this forward checking algorithm is to improvement over the simple backtracking. It's aimed to detect the inconsistent earlier in the search process. Like when a variable is assigned a value, forward checking immediately prompts to the domain of unsigned variables that are connected to the newly assigned variables by the constant, and it removes any values from those unsigned variables domain that would be inconsistent with the current assignments. If we during the pursuing during that it's pruning any unsigned variables, domain becomes empty. It means the current assignment path is a graduated to the lead to the dead end. So this algorithm can then immediately backtrack and rather than continues to the assigned value down to the invalid path. So it is most advantageous to detect the futures earlier and significantly reducing the size of the search tree compared to the basic backtrackings. And we have a constant propagation algorithm. So in this algorithm, concept is to border category of the technique of which forward checking is a simple form. Constant propagation algorithm works by iteratively reducing the domains of variables by removing values that are inconsistent with the constant. The goal is to enforce the different level of consistency across the CSP. Like in extreme constructions, like in extreme constraints and eliminates values for variables and domains cannot possibly be a part of valid. So solution is given by the current state of the domain. When a value is removed from a domain, it might trigger future removals in other connected domains, lead ripple effects of tuning. A common consistent propagation algorithm includes node consistency, ensures that values in a variable's domain satisfaction. So the unary contents, and it has another propagation algorithm includes the or consistence. It is a formula in based. So we can see, for example, we can type every pair of the variable like xi, like hj, and each value of the di. It ensures there existed at least one constant value in dj. If not, the value is removed from the di. So this is applied iteratively until no more values cannot be removed. And we have again in this path consistency and k consistency, more powerful and computationally more expensive from the consistency that involves more variables. So moreover, it advantages has by reducing the search space before or during such constant propagation can improve the efficiency of the finding solutions by eliminating invalid choice of early on it. So usually pre-processing steps are integrated with backtracking, like in this forward check algorithm. So those three approaches are key of to the efficient solving of the complex and large search space inherent in constant satisfaction problems. So I hope you guys this theoretical part you will get understand, and thank you all.